In the last video, we set up a random variable x, which was defined as the number of heads from flipping a fair coin 5 times. And then we figured out the probability that our random variable could take on the value 0, 1, 2, 3, 4, or 5. And just to visualize that, in this video we will actually plot these, and we'll get a sense of this random variable's probability distribution. So let's do that. So let's see, maybe I'll do it like this so that we can see the probabilities. And actually let me erase this business right over here. Whoops, that's not working. Here, that might work. Let me erase this real fast, these little scribbles that I had off screen, and then we can actually plot the distribution. All right, so at one axis, I'm going to put all of the different outcomes. So that looks like a pretty straight line. And then this axis, I'm going to plot the probabilities. And that looks like a pretty straight line. And let's see what the probabilities are. We have, let's see, it's all going to be in terms of 30 seconds, and we get as high as 10 30 seconds. So let's say this right over here is, that right over there is 10 30 seconds. 10 30 seconds. Halfway up there, we have 2 5 30 seconds. So let's see, that looks like about half. That right over there is 5 30 seconds. And then 1 30-second would be about this. It's 1, 2, let's see, how to split it up. 1, 2, 3. Actually, let me do it a little bit. 1, 2, 3, 4, 5. All right, so let's say this is 1 30-second right over here. And our probabilities. So this right over here, probability. So this is what the values that the random variable could take on. So I'll just make a little histogram here. So x equals 0. And then and the probability there, and actually since I want to do a histogram, it will look like this. Actually, let me do a little bit different. So put it right here. So x is equal to 0. Right there, the probability is 1 32nd. And I can shade that in. Now I have the probability that x equals 1. X equals 1 is 5 30-seconds. So let me draw that. So 5 30-seconds. So put the bar there. So let me shade that in. So this right over here is the probability that x is equal to 1, that we get 1. Exactly 1 out of the 5 flips result in heads. Now we have the probability x equals 2. X equals 2 is 10 30-seconds. So that's going to look like this. That's going to look like this. All right. My best attempt at hand drawing it. So somehow I like the aesthetics of hand-drawn things more. Sometimes if you just get a computer to graph it, I don't know, sometimes it loses a little bit of its personality. All right. So that right over there is the probability that we get that our random variable x is equal to 2. Then we have the probability that x equals 3, which is also 10 30-seconds. So that is also 10 30-seconds. So let me draw that. This is also 10 30-seconds. Shade this in. Dum-da-dum-da-dum. All right. I find this strangely therapeutic. All right. So this is the probability that x is equal to 3. Now x equals 4. That's 5 30-seconds. So we go back right over here. That's 5 30-seconds. So shade that one in. So this right over here is x is equal to 4. And then finally, the probability that x equals 5 is 1 32nd again. It's the same level as this right over here. Shaded in. So this right over here is our random variable x equaling 5. And so when you visually show this probability distribution, it's important to realize this is a discrete probability distribution. This is a discrete random variable. It can only take on a finite number of values. Actually, I should say it's a finite discrete random variable. You could have something that takes on discrete values, but in theory it could take on, an infinite number of discrete values. You could just keep counting higher and higher and higher. But this is discrete in that it's kind of these particular values. It can't take on any value in between, and it's also finite. It can only take on x equals 0, x equals 1, x equals 2, x equals 3, x equals 4, or x equals 5. And you see when you plot its probability distribution, this discrete probability distribution, you have it, it starts at 1/32, it goes up, and then it comes back down, and it has this symmetry. And a distribution like this right over here, a discrete distribution like this, we call this a binomial distribution. And we'll talk in the future about why it's called a binomial distribution. But a big clue, actually I'll tell you why it's called a binomial distribution, is that these probabilities, you can get them using binomial coefficients, using combinatorics. In another video we'll talk about, especially when we talk about the binomial theorem, why we even call those things binomial coefficients. But it's really based on taking powers of binomials in algebra. But this is a very, 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 very important distribution. It's very important in statistics because for a lot of discrete processes, one might assume that the underlying distribution is a binomial distribution. And when we get further into statistics, we'll talk why people do that. Now, if you have much more than 5 cases here, if instead of saying that the number of heads from flipping a coin 5 times, you said x is equal to the number of heads of flipping a coin 5 million times, then you can imagine you'd have much, the bars would get narrower and narrower relative to the whole hump. And what it would start to do, it would start to approach something that looks really like a bell curve. Let me do that in a color that you can see better, that I haven't used yet. So it would start to look, so if you had more and more of these, possibilities, it's going to start approaching what looks like a bell curve. And you've probably heard the notion of a bell curve. And the bell curve is a normal distribution. So one way to think about it is the normal distribution is the probability density function. It's a continuous case. So the yellow one, that we're approaching a normal distribution. And a normal distribution in kind of the classical sense is going to keep going on and on. Normal distribution. And it's related to the binomial. A lot of times in statistics, people will assume a normal distribution because they say, okay, it's the product of kind of almost an infinite number of random processes happening. Here we're taking a coin and we're flipping it 5 times, but if you imagine kind of molecules interacting or humans interacting, you're saying, oh, there's almost an infinite number of interactions, and then that's going to result in a normal distribution, which is very, very important in science and statistics. Binomial distribution is the discrete version of that. And one little point of notion, these are where the distributions are, this is where they come from, this is how they're related. If you kind of think about, as you get more and more trials, the binomial distribution is going to really approach the normal distribution. But it's really important to think about where these things come from. And we'll talk about it much more in the statistics, because it is reasonable to assume an underlying binomial distribution or normal distribution for a lot of different types of processes, but sometimes it's not. And even in things like economics, sometimes people assume a normal distribution when it's actually much more likely that the things on the ends are going to happen, which might lead to things like economic crises or whatever else. But anyway, I don't want to get off topic. The whole point here is just to appreciate, hey, we started with this random variable, the number of heads from flipping a coin 5 times, and we plotted it, and we were able to visualize this binomial distribution. And I'm kind of telling you, I haven't really shown you, that if you were to have many, many more flips and you defined the random variable in a similar way, then this histogram is going to look this bar chart is going to look a lot more like a bell curve. And if you had essentially an infinite number of them, you would start having a continuous probability distribution, or I should say probability density function, and that would get us closer to a normal distribution.